So we've been talking about radioactivity and what it is, and some of the nuclear equations. So we're going to learn a little bit more now. So this was a while ago, back in the 1930s. Enrico Fermi tried to make a new element by bombarding uranium with neutrons. The idea was that, maybe we could get the neutrons to stick. Maybe it would undergo beta decay, convert a neutron into a proton, and we could make something new. So he did detect beta emission, but he did not chemically examine the products to see if a new element had been formed. You might think, well, why didn't he do that? It's a lot easier said than done, right? Lisa Meitner, Fritz Strassmann, Otto Hahn repeated Fermi's experiments. And they found that what they got were several elements that were lighter than uranium. And this was a very big deal. This is a discovery that changed the world forever. So January 6, 1939, they reported that neutron bombardment of uranium resulted in nuclear fission, the splitting of the uranium atom. So the uranium atom split into two different elements, barium and krypton, and also gave out 3 neutrons and enormous amounts of energy. That's an understatement. Now this was uranium-235. Less than 1% of the uranium on the Earth is uranium-235. 238 is the most common isotope, and it does not undergo nuclear fission. But this is the reaction for the fission or the splitting of uranium. So we get a barium nuclide and a krypton nuclide, 3 neutrons, and a heck of a lot of energy. If we have a sample that has been enriched in uranium-235, if it has a high enough concentration of uranium-235, we can have a chain reaction occur, where the neutrons given off by this first fission reaction have enough energy and collide with another uranium-235 and cause another fission reaction. So there's 3 of those neutrons. They could each cause another reaction, and then each of those gives off 3 neutrons, which could cause another. And it's, you see how that could go. So that's called a chain reaction, where one thing happens and that causes something else, that causes something else, and so on down the chain. In order for this to keep going, there needs to be a minimum amount, a minimum mass, a critical mass of uranium-235 in order for this to be self-sustaining. But this reaction can be used to make an atomic bomb. So the fear during this time, this is right around the time of World War II, the fear was that Nazi Germany would develop a bomb based on this. And so a group of U.S. scientists persuaded Albert Einstein to write this letter to President Franklin. Sir, some recent work by Fermi and Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable through the work of, I don't know how to say that, Joliot in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements could be generated. Now it appears almost certain that this could be achieved in the immediate future. This phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by boat and exploded in a port might very well destroy the whole port, together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. So as a result of all this, the Manhattan Project was launched in 1941 in New Mexico with the goal of building an atomic bomb before the Nazis did, the Germans did. Any questions about that? I'm not going to quiz you on history, but I think this is a very interesting piece of history. Einstein writing to the president. So that Manhattan Project was successful, and the first nuclear weapon was detonated in 1945. It had the force equivalent to 18,000 tons of dynamite. That's a lot. At that point, Germany had already surrendered. But we still dropped 2 bombs on Japan, killing 200,000 people. We can use fission to generate electricity, and there are numerous nuclear power plants around the world that do this. A controlled fission reaction can be used to generate electricity with no air pollution, no production of greenhouse gases. At the writing of this edition of the textbook, nuclear reactors provided about 20% of U.S. electricity and up to 70% in some countries. A pencil-sized cylinder of uranium of the appropriate enrichment could power a typical car for 20 years, something this big. Run your car for 20 years. It's a little mind-boggling. Another little factoid here, a coal-burning power plant would use 2 million kilograms of fuel to generate the same power as 50 kilograms of fuel would generate in a nuclear power plant. So, yes, question?
Can it only be uranium, or can they use whatever they want?
That's a good question. Could it be something other than uranium?
Hydrogen is a bomb.
I think, yeah, but that's something different. I don't, I'm sure that it's possible. I don't know if anyone has explored things like that. I think this is the best option.
Is it just easier with uranium?
It's easy, yeah. Yeah. There's a lot of factors involved. You have to get those neutrons generated so that they go on and make other things happen, and yeah. So how does a nuclear fission reactor get converted, or reaction get converted into electricity? So here's a sketch of a nuclear power plant. So here we have the reactor, and in the reactor there are different rods. There are fuel rods and control rods. The fuel rods are the enriched uranium-235, and the coal rods, control rods, are often graphite. They're a neutron-absorbing substance. So you can control this reaction by raising and lowering the control rods. When you lower the control rods, they will absorb the neutrons without undergoing fission, and so you can slow things down. Because the problem with this is it can get out of control, right? And then you have a bomb. Not good. So this is generating a lot of heat. And so this heat is used to heat water, and we get steam forming, and that steam can be used to turn a turbine in an electrical generator. So there are many great things about nuclear power. Unfortunately, there are 2 significant drawbacks: nuclear accidents and waste disposal. Any questions yet? So nuclear accidents are a problem because a fission reaction can overheat in spite of safety precautions. Thank you. Okay, they can overheat. So a famous nuclear accident occurred in 1986 in Chernobyl, which is in Russia. They were doing an experiment in which they were trying to reduce maintenance costs. And so safety features were disabled. The experiment did not go well. And the nuclear core, which was partly graphite, overheated and began to burn. This was just massive, massive failure. There were 31 immediate deaths, and a 32-kilometer radius became uninhabitable, and it's still not inhabitable. Another nuclear accident occurred in Japan in 2011. There was a tsunami triggered by a massive earthquake. The Japanese had prepared for earthquakes. But in this case, the tsunami came in and washed over the whole place. And there's a cooling pond where water gets pumped into the reactor and comes back out to cool off. And they had generators to keep the pumps going because the electricity, was cut off. They had generators to keep the pumps going, but they did not account for all the gunk that got into this pond, which gummed up the pumps and caused them to stop working. So then we've got not enough water in the storage ponds that can be pumped through, and so the fuel also was overheating. The radiation release there was significant, but it was much lower than at Chernobyl, and at least according to the textbook, no radioactivity-related deaths were reported. So it seems like we've gotten better at nuclear accidents, at least. Neither of those incidents was a detonation, a bomb exploding. The uranium fuel that they use in the reactors is not enriched enough to actually explode like a bomb would. The U.S. has nuclear plants. They have a lot of safety features designed to prevent such accidents. Of course, unforeseen things happen. But overall, I would say nuclear power has gotten a bad rap. It has some drawbacks, but the other ways of producing electricity also have some significant drawbacks. So another problem besides the accidents is disposing of the nuclear waste. The amount of fuel is small compared to other sources of electrical generation, but some of the products here are radioactive and they have long half-lives. And so we can't just, dump these in the ground somewhere. They need to be stored safely. They were going to make a permanent disposal site in Nevada, but that got stopped in 2010. As far as I know, they're still talking about that. So currently, at each reactor, they're just storing the nuclear waste on site.